Okay, so we are going to get right into our next lesson, which is on intersections of polar equations. We are going to be looking at this visually, so graphically, we'll see how these polar graphs intersect with one another. And then we'll also look at how we actually find those points by algebraically and using our knowledge of trigonometry in order to find these intersection points. So we'll start with a couple of things that we'll need to know before we get right into some examples. So to find the intersection of two polar graphs, we may need to take into account some properties. So we'll have to remember that first of all, r comma theta and r comma theta plus 2 pi give the same point. So for our purposes, we are just going to assume that the period for our polar graphs is 2 pi. Second thing that we will try to take into account, if we might need it, is that 0 comma theta gives the origin for all theta values. Now this will come in handy, particularly when you're looking at it visually, and you might end up seeing that the origin might be a point of intersection. Now when you solve it algebraically, you might not necessarily get that just because of this property that 0 comma theta actually gives you the origin no matter what theta value is. So it's definitely something to keep in mind. All right, and the third thing is that r comma theta and negative r comma theta plus pi give the same point. Now this takes us back to when we just started polar graphs and we were talking about polar coordinates and how you can find different ways of writing the same coordinate in polar form. So if you remember, if you had r comma theta and you were trying to find three different versions between negative 2 pi and 2 pi, one of the ways to go about finding the same point was to take a negative r value and you would just add pi or subtract pi. So just note that this is the case. It may be useful, particularly when you've already tried to solve, but you know that there are more points. By doing this, by using this information, you may be able to find other points that you weren't able to find the first time around. So set equations equal to each other. You'll change one side of the equation to the opposite sign and change the angle measure, if applicable, to theta plus pi. Okay, so here's the first example. We'll try to keep it simple to start. We'll get a little bit more complex later. So find the intersection of the graphs r equals 1 and r equals 2 cosine theta. Okay, so for the first one, r equals 1, you all know that that is going to be simply a circle with radius 1 that is centered at the origin. Okay, and then r equals 2 cosine theta. Now this takes us all the way back to circles. So remember, this is a circle that is centered at 1, 0, right? It's 2 times 1 cosine theta, right? It's twice whatever that radius is. So r equals 2 cosine theta means it's going to be centered at 1, 0, has a radius of 1. So here's what that looks like. Now, if you're taking a look at these two graphs, you can probably pretty easily see, oh, there are two places where it intersects, right? And I'm going to put them here in yellow. So there's one point up here, one point down here. So we know that we should have two answers. So now, how do we go about solving this algebraically? Well, the two equations that we were given is r equals 1 and r equals 2 cosine theta. So since they're both in the form r equals and r equals, we can just simply set them equal to each other. So 2 cosine theta equals 1. And if we get cosine theta by itself, we have cosine theta equals 1/2. Now that looks really familiar from our trig units. Solve for theta. So you know that cosine is equal to 1/2 when you have the reference angle of pi over 3. It is positive in the first quadrant, and it is also positive in the fourth quadrant. So that would be at pi over 3 and 5 pi over 3, which if you look at this corresponding to our graphs here, right, there's one point that is in the first quadrant and one point that is in the fourth quadrant. So we're on the right track. So the last thing is to make sure that when you are giving your answers, just like when you were solving a system of equations, you always had to give the answer in the form x comma y, or x equals and y equals. So same thing here. We have 2 points. We have what theta is equal to, but we also need to know what r is equal to. Now for some of these, r is going to be pretty easy to find. In this particular case, one of them was already given to you. R is equal to 1, right? So you actually know that since both of those intersection points are exactly on that circle of radius equal to 1 that is centered at the origin, you actually know that r is equal to 1. So your two answers are 1 comma pi over 3 and 1 comma 5 pi over 3. Those are your two answers. Now in future problems, you might not get something as easy as it's already given to you what r is equal to. In those cases, you'll take your values of theta and you'll plug them in to get your r value. Sometimes you'll end up with the same r value in both cases. Sometimes you might not. It really just depends on the types of polar graphs that you're given. All right, let's take a look at example 2. Find the intersection of the graphs r equals cosine theta and r equals 1 minus cosine theta. Okay, so just even looking at the forms of the graphs, of the equations, you can know what the graphs are. So the first one we know is going to be a circle that is centered at 1/2 comma 0 with a radius of 1/2, right? So there's r equals cosine theta. And the second one, r equals 1 minus cosine theta, that should look familiar. It should be in the form of a limacent. And in particular, this is really 1 minus 1 cosine theta. So this is in particular actually a cardioid. So this is a cardioid that is going to extend, so because it's cosine, it's going to be symmetric with respect to the x-axis. We know it's going to extend out to the negative x-axis, out to -2, and it's a cardioid, so it's going to have that, well, I won't call it a dimple because that's a different type of limacent, but it's going to have a point right at 0 and make that heart shape. All right, so now we can take a look at this and we can see that there are, let's see, there's one intersection point over here, there's one over here, and there's actually one more, and that's right here. So there are 3 points of intersection. So now let's go ahead and try to find those 3 points of intersection algebraically. So first we have r equals cosine theta and r equals 1 minus cosine theta. But we are going to go ahead and set them equal to each other since they both are in the form r equals. So cosine theta equals 1 minus cosine theta. And we will go ahead and add cosine theta to both sides to get 2 cosine theta equals 1. Divide both sides by 2. And then now we can write out what theta has to equal. So with theta equaling, with cosine theta equaling 1/2, theta has to equal pi over 3, that's the first quadrant, and 5 pi over 3, that's the fourth quadrant. Okay, now what are the r values? So unlike the first example where you were given r equals 1, in this case, we have to plug it back in to one of those equations. Now, it doesn't matter which equation you use, just like a system of equations, doesn't matter which one you plug it back into because they intersect at that point, so they share that point. So when theta is equal to pi over 3, I'm just going to use the first one because that's a little simpler. So we have cosine of pi over 3, which is equal to 1/2. We have r equals cosine of 5 pi over 3, which is also equal to 1/2. So we have 1/2 comma pi over 3, 1/2 comma 5 pi over 3. Now wait a minute, we said that there were 3 intersection points. But right now we've only written down 2. So if you take a look, we did get the one that's in the first quadrant, the one that's in the fourth quadrant. The one that we don't have is the point right at 0, 0. So this is one of those things you have to remember. Because 0 comma theta, theta can be anything, and you would still get that point. It's important, now you might be able to see why it's important to actually draw out what the graphs look like so you don't miss any of the intersection points. So in this particular case, we have 0, 0 as well as an intersection point. Right, and those are all 3 of the intersection points for this example. All right, let's take a look at example 3. Find the intersection of the graphs r equals 2 sine of 3 theta and r equals the square root of 3. Okay, so r equals the square root of 3. I know it looks intimidating just because it is square root, but this is really just r equals a number, which you know this is going to simply be a circle with radius of square root of 3 that is centered at 0, 0. So square root of 3 comes out to be about 1.7, so we'll just sketch what that looks like here. And then for the equation on top, r equals 2 sine of 3 theta. This is a rose curve that has petals that are of length 2, and because it's sine, we know that there is symmetry with respect to the y-axis, and because we know that n is odd, it's 3, we know that there are going to be 3 petals. So we can go ahead and draw this in. Okay, so now let's see where our intersection points are. It looks like we have 1, 2 here in the first quadrant. We have a third one here in the fourth quadrant, fourth one here, and then 2 more in the second quadrant. Okay, so it looks like we have 6 intersection points to find for this problem. Okay, so let's go ahead and set those 2 equal to each other. Again, they're both in the form r equals, so maybe you can now see why we learned all the different forms in the form r equals. So we have 2 sine 3 theta equals the square root of 3. We're going to divide both sides by 2. All right, so now we have sine of 3 theta equals root 3 over 2. Now this is if you remember back in our trig chapters, we talked about multiple angle type of trig equations. All right, so this is one of those examples. So what does that angle measure, 3 theta, have to equal in order for us to get root 3 over 2? So 3 theta is going to have to be pi over 3, right, plus or minus 2k pi. It could also be in the second quadrant, so 3 theta could also equal 2 pi over 3 plus or minus 2k pi. And then we'll get theta by itself in both of these, so we'll divide both sides by 3. So we have pi over 9 plus or minus 2k pi over 3. And then the second one, theta equals 2 pi over 9 plus or minus 2k pi over 3. So from here, if you recall, we're trying to find all the values between 0 and 2 pi. So we know that pi over 9 is a value and 2 pi over 9 is also one as well. But remember, with multiple angles, we know we should have 3 times that number. Right now we have 2, we have 3 times that, which is 6, which makes sense because we have 6 intersection points. So we should be able to find 4 more angle measures that are between 0 and 2 pi. So take that first one, pi over 9 plus or minus 2k pi over 3, plug in 1 for k, so you're adding 2 pi over 3, which is the same as 6 pi over 9, so pi over 9 plus 6 pi over 9 is 7 pi over 9. Okay. Do the same thing in the second one, 2 pi over 9 plus, well, 6 pi over 9, so that's 8 pi over 9. All right, and then when k is equal to 2, we have 4 pi over 3, 4 pi over 3, which is equal to 12 pi over 9. Add that to pi over 9, we get 13 pi over 9. Do the same thing to the second one, 2 pi over 9 plus 12 pi over 9, which is 14 pi over 9. Now, what is r equal to? Well, r is equal to the square root of 3. And if you look at the graph itself, right, all of those points are on that circle that's centered at 0, 0. And when that happens, it actually makes it much easier because you know that all of those points are going to have a value of r equaling to whatever the radius of that circle is, in this case, square root of 3. So your answer is root 3 If you plug it in, you get the same thing as well. So root 3, comma, pi over 9, root 3, comma, 2 pi over 9, root 3, 7 pi over 9, and so on, until you have all 6 points. And you can double check and make sure that all these points do in fact make sense, that you do in fact have pi over 9 and 2 pi over 9 that are in quadrant 1, 7 pi over 9 and 8 pi over 9, which are in quadrant 2. You have 13 pi over 9, which is in quadrant 3, and 14 pi over 9, which is in quadrant 4. So you have all 6 of the intersection points here. All right, last example. Find the intersection of the graphs r equals 1 minus cosine theta and r equals 1 plus sine theta. Okay, so if you look at the forms of these two graphs, you'll notice they're in that form a plus or minus b cosine theta or a plus or minus b sine theta, which means that these are limicons. In particular, the one with cosine is going to have symmetry with respect to the x-axis. It's a minus in front of it, so it's going to extend out to the negative x-axis, and the plus sine theta is going to have the symmetry with respect to the y-axis, and it's going to extend out to the positive y-axis. Okay, so let's go ahead and draw those. And here we know that both a and b are equal to 1 in both cases, so we actually know, in particular, not only do we have limicons, but we actually have cardioids. So here's the first one, 1 minus cosine theta, and 1 plus sine theta. Okay, let's look very carefully where our intersection points are. So it looks like we have one out here. And we look very carefully in here. I know it's very small, but we actually have 1 point right here and 1 point right here. So we actually have 3 points of intersection. All right, let's go ahead and get into algebraically solving this. So we'll go ahead and set those two equal to each other. 1 minus cosine theta equals 1 plus sine theta. Now we have a 1 on both sides, so we can just subtract that or cancel it from both sides. Leaves us with negative cosine theta equals sine theta. Okay, let's try to get it down so that we only have one trig function we have to deal with. All right, it's not very useful to have it in terms of two trig functions. So if we divide both sides by cosine theta, we end up with negative 1 on the left, and we have sine over cosine, which you all know is equal to tangent. So tangent theta is equal to negative 1, and now we have something we can work with, right? So tangent, remember, is equal to 1 when the reference angle is pi over 4. It is negative in quadrant 2 and in quadrant 4. So that would be at 3 pi over 4 and 7 pi over 4. Okay, so remember that r is not always equal to the same thing. And if you look at this particular example, right, it's not that all those points are on the same circle with a certain radius, right? In fact, we're working with two cardioids. The point that's at 3 pi over 4, right, the one in quadrant 2, looks like it's much further from the origin than the one that's in the fourth quadrant, right? If you look at the one in the fourth quadrant at 7 pi over 4, that looks like it's really, really close to the origin. So these two r values are going to be different. So how do we figure out what the r value is? We still plug it in, but we plug in both individually, right? Because we have, we're going to have two different points. So the first point is 3 pi over 4. If we plug that right in, I'll pick the first equation, for example. It doesn't matter which equation you pick. You should get the same thing. We have r equals 1 minus cosine of 3 pi over 4. Now cosine 3 pi over 4, you know, is equal to negative root 2 over 2. So this ends up being 1 plus root 2 over 2. Okay, now for the second one, when theta is equal to 7 pi over 4, again, it doesn't matter which equation you pick, just plug it into one of them. We'll keep with the one on top. So r equals 1 minus cosine of 7 pi over 4, and you know that cosine of 7 pi over 4 is equal to positive root 2 over 2, which means this is 1 minus root 2 over 2. So you'll notice between these two, the r value for 3 pi over 4 is much larger than the r value for 7 pi over 4, right? One's 1 plus root 2 over 2 and one's 1 minus root 2 over 2. Okay, so we can write down those points. We have 1 plus root 2 over 2, comma, 3 pi over 4. And we have 1 minus root 2 over 2, comma, 7 pi over 4. Now remember, when we first drew these and we looked at the intersection points, we said there were 3. If you'll notice, that third one that we don't have written down is the one right at the origin, so that is our third intersection point at 0, 0. And those are all 3 intersection points for this last example. All right, so those are all the examples we have for today. Hopefully this gives you a good idea of how we can relate both the graphical aspect to the trigonometric aspect, be able to use both and see the usefulness in both having the graphs, being able to see, being able to visualize where those intersection points are, and then how do you actually calculate those intersection points using those trig equations, using what you learned from your trig chapters to find your theta values, and then plugging those back in to find your values of r. All right, and that's all we have for today.